Okay, there we go. And I'll be presenting my work on N4, which was an N-polymer realigner for improving pileup-based variant calling for nanopore sequencing. So before I start talking about my project, I'm going to do about 15 minutes of background because I'm sure everyone has differing levels of experience. Talking a little bit about whole genome sequencing, then nanopore sequencing, and finally some breed alignment and variant calling. So whole genome sequencing, just an overview of the whole pipeline. And in this example, it will be viral genome sequencing, although it's the exact same pipeline for human genome sequencing. You'd start with a nasal swab for your sample. For humans, it might be a tissue sample. And then you do some kind of laboratory prep to isolate the DNA. With a virus, you might be starting with RNA and reverse transcribe it to DNA. But in the end, you have your DNA. And then you use that as input to a sequencer. And I'll be talking about nanopore sequencing. So this is their small handheld device, the MinION. The output of that is a raw current signal, which then using a machine learning tool called the base caller gets converted to a string of ACGT. So you're going to get strings of ACGT, anywhere length from 100 to 1,000,000 bases long. And basically nanopore sequencing can read fragments of DNA that you'll need to use to figure out the actual genome sequence. So the next step is aligning these reads to your reference genome in order to figure out where they came from. And the last step is going to be variant calling, where you identify differences from the expected reference genome with the measured actual reads. So here we can see this A was mutated to a C, and we are going to mention that in our final variant calling. So my project in particular is focusing on this alignment stage, and it's trying to align reads more consistently in order to help the downstream variant calling step. A little bit farther back in the pipeline with sequencing, there's kind of a few major players. There's even more in recent years, but kind of the industry standard has been Illumina short read sequencing, where each read is 100 to 1,000 bases. They've always had really good accuracy, and they're currently one of the most cost-efficient options. More recently, Oxford Nanopore and PacBio have become major players. The main benefit of Oxford Nanopore reads is that they can get incredibly long, and they've done a great job improving their accuracy in recent years, from like 90% to 99 to 99.9%. And the main benefit of having such long reads is that they can unambiguously map to the reference genome and even span long, incredibly repetitive regions. And once you have long reads, you can also use that to phase variants on each of the two haplotypes and figure out which variants came from the mother or father in the case of germline variants. And PacBio reads are a little bit shorter than nanopore reads, but still pretty long. And they're great for their accuracy in repetitive regions of the genome, where nanopore sequencing sometimes struggles. So for this project, I focused on nanopore sequencing as the technology. And now I want to mention that when you're doing the alignment, there's actually different options for doing this. You can either use a known reference genome and align your reads to that reference, or you can start from scratch and identify the prefix and suffix overlaps within your read and construct a genome from scratch. And I'll be focusing on reference-based alignment. So now in terms of applications, there's a whole load of things you can do with this. You can figure out the exact strain of viruses and bacteria for contact tracing, figuring out antibiotic resistance. You can do any kind of patient diagnoses for rare genetic diseases or cancer. And there's also existing work on predicting drug response to certain treatments based on the unique genetic profile of each patient. So now on to how nanopore sequencing works. Basically, you start with an ionic solution and you take a membrane that splits it into two compartments. The next thing you do is you apply a voltage across this membrane. So any ions on one side of the membrane are going to want to move to the other side of the membrane because they're charged. At the moment, they can't because the membrane's in the way. So what you do is you embed a small protein channel or a nanopore into that membrane, and that allows ions to move from one side of the solution to the other through the nanopore. Now, if you put DNA on one side, it's also going to want to move to the other side because it's charged as well. And as this DNA moves through the pore, the bases of the DNA end up altering the rate of ion movement through the pore because they're both trying to move through simultaneously. So what you can do is you can measure the current over time, and you can figure out which bases of the DNA are currently obstructing the pore based on your measured current. So in a very simplistic view, there might be 4 different current levels for each of the 4 possible bases. And based on the current over time, you can figure out the DNA sequence and read your whole read. Now, in reality, the signal's a lot messier. You can see it's a little bit noisier. And in reality, instead of the current level being affected by a single base, it's actually affected by around 5 to 6 adjacent bases, because that's how large the constriction in the nanopore is. So instead of having 4 possible current levels, you actually have 4 to the 5th or 4 to the 6th. So you need a lot of machine learning in order to figure out what the actual sequence was from your raw current trace. And I'd like to mention right now that one issue that nanopore sequencing runs into is if you have a repetitive DNA sequence. Because the current level is affected by only 4 to 5 bases, if all those bases are the same, as you shift over one base at a time, the current level is going to stay pretty much the same. So if you have a long repeated region, it's really hard to identify the transitions from one base to another and know how long that repeated region actually is. So here we can see some example reads aligned to the reference genome, and we can see that it gets the length of this repeated sequence of A's incorrectly a lot, relatively frequently. So now on to the bioinformatics part, the read alignment. The simplest way to align reads is with edit distance. Edit distance is the minimum number of edits required to transform one string to another. And in this case, the 2 strings are our expected reference genome and the read that we just sequenced. And edits can take the form of substitutions, where one base is changed to another, insertions, where we gain an additional read base that was not in the reference, and deletions, where we lose a base that was in the reference, but is not in our sequenced read. And now it's important to note that a lot of times there's many possible alignments for the same 2 sequences, even with the same minimum edit distance. So in this example, the insertion could have happened here, or it could have happened one base prior, or even this insertion and deletion could have just been 2 substitutions. And what we want to do with our alignment is actually end up with the alignment that best represents what probably happened. And we want that to be consistent across reads so that we can identify which mutations are actually present in the sequence. So now, in order to calculate this edit distance and find the optimal alignment, imagine that you're aligning your reference to your read, and you've already aligned some prefix of your reference to some prefix of your read, and you have some remaining reference bases and some remaining read bases, and a pointer to the first of each of those. Now, when you're trying to align the next few bases, you have 3 different options. So ignoring what you've previously aligned, the next base could either be just the base in your read, which would be an insertion, or it could be just the base in your reference, which would be a deletion, or it could be both bases in both your read and reference. And if they happen to be the same, it'll be a match. And if they're not the same, it'll end up being a substitution. So at each position, as you walk through the reference and read bases, you have 3 possible options. So there's 3 to the R possible alignments, where R is the minimum length of your read and reference. So this is a lot, and in order to find the minimum edit distance, we don't want to have to walk through all possible alignments. So how can we do this more efficiently? Fortunately, the edit distance is independent of the prefixes that you've already aligned. So if we've already aligned the first 4 bases of the reference in the read. Then if we have an insertion, it's just going to be that edit distance plus 1. If we have a deletion, it's going to be that edit distance plus 1. If we have a match, the edit distance will stay the same. And if we have a substitution, the edit distance again increases by 1. So we can use dynamic programming to store the best possible alignment of our read to our reference for each of the possible prefix lengths of both the read and the reference. So what we end up with is a matrix that contains all the possible prefixes of our read and our reference. So at this highlighted position, we've aligned the first 4 bases of our read and the first 4 bases of our reference. And as I showed in the previous slide, from here we have 3 possible options. We can align 1 more base in the reference, which would be a deletion. We can align 1 more base in the read, which would be an insertion, or we can align the next base in each of the 2 sequences, which would either be a match or substitution. In this case, insertions and deletions increase the score, and a match does not. Actually, it's a little bit easier to flip this around, and looking at this position, look at the 3 possible positions we could have come from. And again, considering the score increases for each of those movements, as long as we take the minimum, then we can get the score for the best possible edit distance up to that point for this prefix of the read and this prefix of the reference. And at the end, after walking through the entire matrix, this final cell will be the minimum edit distance for aligning the read to the reference. Now, the only problem with edit distance is that it doesn't account for the fact that 1 insertion or deletion is going to be much more likely than the summation of multiple smaller insertions or deletions. So in these 2 examples here there was an insertion of 3 bases. Here there was an insertion of 2 bases and an insertion of 1 base. And according to this, the 2 edit distances are the same. They're both 3. However, the one on the left is much more likely. So in order to account for this and to prefer this alignment on the left when we align the reads, affine gap scoring was invented. And this is known as the Smith-Waterman or Needleman-Wunsch algorithm. And basically the idea is that instead of having 1 state matrix, you end up with 3. So the first state matrix is you're in the normal state, you're aligning bases to one another, and then you have an inserting state where you're currently inserting bases, or a deleting state where you're currently deleting bases. Now, if we look back to the transitions I mentioned earlier, if you're starting in this cell, you can perform either a match or substitution moving diagonally, and there's no penalty if the next 2 bases match, but there is a penalty if the bases mismatch. But we are also allowed to start an insertion or a deletion. And here we raise this to be a relatively large penalty. So inserting a base might be a penalty of 5, and the same thing if we're starting a deletion, whereas a substitution will only cost 3. However, once you're already in the insertion state, you can continue making further insertions for a lesser penalty. And then you can move back to the normal state and end the insertion for no penalty at all. And the same thing in the deletion state. Once you've started deleting bases, you can continue deleting bases at a lower penalty, or you can transition back to the normal state. So what this does is basically there's an increased penalty for each time you start an insertion or a deletion. So because you started 2 different insertions here, you're going to get penalized twice for entering that insertion state. Whereas here, you're only going to get penalized once for entering that insertion state. So the alignment on the left is going to be preferred. So now on to variant calling. For nanopore sequencing, this is typically done in 2 steps. So the first step is known as pileup calling, whereas a pileup is the alignment of all your reads to the reference, all piled up against one another. And this first stage is just to identify candidate variants. So within a small window, it looks at each reference position, what bases are aligned to those positions, A, C, G, or T, and using those summary statistics, it figures out whether or not there's likely a variant relative to the reference. And in this step, which is where current nanopore sequencing variant calling struggles, it's important that the alignments are consistent so that all of the changes to the reference sequence are reported in pretty much the same place. Otherwise, you're not going to realize that there was actually a mutation there. And the second step is full alignment calling, where basically instead of just looking at a narrow window, you look at a much wider window, and you have higher dimensional information about the reads in order to do the final variant calling. And we're focusing on improving the alignment so that we can identify a better set of candidate variants during this pileup calling stage. And this is kind of what the input looks like in one of the current tools called Pepper. It's encoded the reference genome in these 4 colors, and then forward mapped ACGT and reverse mapped reads. The color basically represents the proportion of reads which support that base at each position. And in general, they agree with the reference. But for example, at position 23, there's a little bit of disagreement on whether the base is green or red, so in A or T. And then using a sliding window approach, we decide at each position whether or not there's a variant using a convolutional neural network. So now on to what my alignment. Yep. What'd you ask? How they basically like determine.
Does it take account of this particular protein or this set of proteins?
Yeah, so
just a general proportion of the nucleotides of the whole gene.
yeah, so this does so this input here is like an image, which is going to be an input to the network, which basically decides for each position in a sliding window. So this purple window here will refer to this one position on the reference. And it's trying to decide at this position, is there a variant or not? So these color values, these are the encoded reference bases. And then each of the other rows are the proportion of read bases once you've aligned all the reads to the reference. So here we've aligned all the reads. You count basically the number of A's, the number of C's, G's, T's, and deletions at each position. And then you increment the values in each of these correspondingly. And it uses this small image basically to try and make a binary classification of whether or not the reads support a different base than what the reference says is contained at that position. Did that answer your question or no?
Well, not quite. I just need to on. Is that an analysis for this gene only?
This is done across the entire genome. Yep.
Tim, there are questions asked in the room. If you're able to repeat them for the people online, that'll help them hear it a little better.
Okay. Okay, so now on to the motivation for my algorithm. But before talking about the motivation, I want to clarify a definition. So in the title of my talk, I referred to N polymers, but more typically, repeated sequences are referred to as homopolymers or simple tandem repeats. I referred to them as N polymers just to simplify it so it's more succinct. So if you have a 1 nucleotide repeating sequence, I call it a 1 polymer instead of a homopolymer. If you have a 2 nucleotide repeated sequence, I call it a 2 polymer instead of a simple tandem repeat with repeat length unit 2, and so forth. If we have a 3 nucleotide repeating sequence and so forth. And the next important definition to know is copy number. So I've already defined N as the length of the repeat unit. So it's 2 bases that get repeated. And then the copy number, the expected number L, is the number of times that this repeat unit length is repeated. So L is the expected length from the reference, L prime is the measured length from our read. And here we can see that GA was only repeated twice. Okay, so now the main motivation for this whole project was the fact that for nanopore sequencing, basically they split the evaluation into SNPs and indels. So SNP is a single nucleotide polymorphism, or basically a substitution mutation, where one base is changed to another. And an indel is either an insertion or deletion, where bases are either added or missing from the reference. And now for nanopore sequencing, the accuracy performs very well on SNPs with high precision and recall, but for insertions or deletions, it has much lower precision and pretty much abysmal recall. And as I mentioned earlier, this is largely due to the fact that it struggles in repetitive regions. So here we can see, as I mentioned earlier, the current level is affected by multiple bases at a time. And so when you have a lot of bases that are the same repeated after one another, your current trace is going to stay relatively flat, and it's hard to detect transitions from one base to another and know how long this sequence actually is. And here are some statistics for how frequently it gets it wrong. So these are confusion matrices for one polymers. So it would be a single base that gets repeated. And then the percentage of time that in each square, the actual length was called the predicted length. So if we have 3 A's in a row, we'll get it right 96% of the time. But if we have 10 A's in a row, we'll only get that right like 58% of the time. And if you look at repeated sequences with a larger repeat unit, say 3 bases, it does a little bit better, starting at 98%. But as we move on to longer repeat lengths, we see the same trend. It progressively gets worse with around 87% accuracy. And further, I want to point out that these insertions and deletions in N-polymer regions are very important. And they're a large fraction of both the calls that we get wrong when variant calling and also the true insertions and deletions. So on the very left, we can see the different variant call types. There's mostly substitutions, a few insertions, a few deletions, and then very few complex variants. And we can see that almost all the substitutions we got correct. But if we look at the false positive and false negative variants, the majority of them stem from incorrectly calling insertions and deletions. And if we then blow up these errors to look at all the mistakes we made, then I categorized the genome into different regions. So other is any kind of non-repeating region in the genome. One polymer is when you have the same base repeating and so forth. So we can see that in the genome, the vast majority of it is non-repetitive. So even though more than 50% of the genome is non-repetitive, that only accounts for less than 10% of the total errors. And any of these repetitive regions with repeat unit length 1 to 6, they're vastly overrepresented in terms of the errors that we end up making. And then if you look at the true insertions and deletions, so this is based on some form of variant calling ground truth against a reference genome, we can see that again, the repetitive regions are overrepresented. So actual insertions and deletions are fairly likely to be copy number variants of these repetitive regions. And general indels are much less likely in general. So the main motivation for this project is the fact that alignments end up being inconsistent if you use the gap affine scoring that I mentioned previously, because that doesn't account for the fact that getting the lengths of repeated regions wrong is very common for nanopore sequencing. So here we see a bunch of A's and a bunch of T's. And if we say there was an extra A and one fewer T's, then it's going to choose to place it as a substitution at this position, Whereas if we say there was an extra A but no extra T's, it's going to choose to left align an insertion at the start of all the A's. And then if we have 2 extra A's and 2 fewer T's, then we're going to see substitutions at position 7 and 8. So the issue comes later when you try and do the variant calling and you have these pile up summary statistics per reference position. And even though there was an extra A in all 3 of these cases, when you look at position 2, you're only going to see 1 out of 3 had an extra A. And then you're going to see 2 out of 3 substitutions at position 7. So because the alignment isn't really that consistent, there's no one position where there's clearly an insertion or a deletion. And that's why, to some extent, the variant calling struggles with insertions and deletions. And as I mentioned, the alignment doesn't really reflect the probability that substitutions and insertions and deletions are actually happening, because your scoring matrix and functions are totally static everywhere on the genome, and they don't account for the fact that insertions and deletions are orders of magnitude more likely in repetitive regions. So at the moment, you have this one substitution penalty matrix, where if you mess up any of the calls, you have this penalty score, and for insertions and deletions, the cost is always going to be the same, whether you're adding an A to a sequence of 20 A's, or whether you're adding an A in a non-repetitive region. And that's kind of the issue with the current alignment. So now I'm going to talk a little bit about my algorithm, what I changed to improve this alignment. And basically, I instead calculated the actual probabilities. So on the left over here, I have a confusion matrix, and this is the count in millions of all the reads that I aligned to a genome. And I counted every time that the reference said there was an A, and our read said there was an A, and the same thing, our reference said there was an A, but our read said there was a C. And then I have the measured probabilities of all of these different errors. And now on the right, I converted these to penalty scores using the negative log probability of one base being called another. So basically, I just divide the number of times an A was called a C by the summation of that entire row. So given an A, what's the probability that it was called a C? And then I take the negative log probability of that. And the nice thing about this is that when you're doing the alignment and you have multiple substitution errors, as you do the alignment, you sum the penalty scores. And if you're looking at statistics, the probability of 2 independent events both happening, you take the 2 probabilities and you multiply them. But by shifting this over to log space, multiplication is the same as addition. So by calculating the actual probabilities in log space and then adding them as we do the alignment, what we're actually doing is calculating the most probable alignment or sequence of edits that actually happened given the measured profile of these errors in our data set. So we changed the substitution scoring matrix a little bit, and same with the insertion and deletion penalty in general, but the main improvement was adding a lookup table based on the actual rates of certain length N polymers getting called other lengths. So again, we did the similar error probability calculation, where if a repeat unit is of length N, and it was expected to be length I, but it got called length J, then we calculate for each of those possible repeat unit lengths, what our penalty score should be for accidentally adding an A or dropping an A, and so forth. So we end up with these score matrices for each of the different N polymer lengths. So homopolymers, if you have one repeated sequence, if you have 4 A's in a row, actually, but you call 3 A's, then you have a slight penalty for doing so. But if you had 10 A's in a row and you called 9, this time you still dropped 1 A. It's the same change, but the score is lower because it was measured to be much more likely to occur based on the statistics in your data set. And then if you have a longer repeat unit length, again, things are similar, but the scores are a little bit higher because it's less likely to lose a copy of AAC than to just lose a copy of a single base. And we can see, interestingly, that losing a base, so bottom left of the diagonal, generally has much lower scores than the upper right or adding bases, because as I mentioned, the nanopore signal stays relatively constant in repetitive regions, so it's difficult to detect transitions. So it generally ends up underestimating the number of bases that there are. So this does end up complicating the alignment algorithm. So instead of having one table with edit distance or 3 tables with affine gap scoring, now we end up with 5 different state tables. So we have M for when you're in the matching state, I and D for inserting and deletion. But now we also have tables L and S for lengthening and shortening these repetitive regions. So for each matrix, I've marked with a symbol according to that matrix. So if we're in the match state and we're computing this cell with the star, then the star superscripts represent possible predecessors. So if we're at position I and J in our read and reference, and we're trying to calculate the score at this state, then we move one previous base in the read and reference, and we take our substitution penalties for converting this reference base to this read base. And that's one possible predecessor. The other possible predecessors are leaving the deletion, insertion, shortening, or lengthening states, each with penalty 0. And then, as I mentioned earlier, for the affine gap scoring, if we are computing cell IJ in the insertion state, you can either be extending a previous insertion for a lower penalty or starting an insertion with a higher penalty from the match state and so forth. And then for lengthening and shortening, things are complicated because you have to look a number of cells back depending on what your repeat unit length is. But basically, it allows jumping there from that state based on looking up the score for that error in the penalty matrix. And these transitions are only allowed if certain conditions are met. And those conditions are basically enforcing that we're only going to allow these transitions when we are in an N polymer at the start of a repeat unit. So this allows adding and dropping individual repeat units based on the scoring in that lookup matrix. And then there's some nice properties of having this additional possibility for transitions. So first, the penalty will depend on what your expected and measured length was going to be. So here we can see if the expected length is 3 A's versus 5 A's versus 8 A's, the penalty for dropping 1A if you only started with 3 is higher because it was less likely. But as the length of homopolymer increases, your score for dropping an A decreases because that's more likely. And then I'd like to mention that the penalty depends on the length of the repeat unit. So losing a base from a homopolymer is more likely than losing 3 bases from an N polymer with N equals 3. And I only allow inserting or deleting like one entire unit at a time. And then another thing to note is that the actual sequence isn't really considered. So for a given repeat unit length, so here the repeat unit length is 3, and there's 3 copies. I'm not actually looking at what the underlying sequence is. I'm just saying this is kind of the repeat pattern and assigning penalty scores based on that instead of breaking it down by each possible sequence, because for unit length N, there's 4 to the N possible sequences, and quickly that kind of grows out of hand. And then this alignment does allow considering overlaps. So if there's kind of nesting with one repeated sequence within another repeated sequence, we can handle that. Last thing to mention was that I did do some banded alignment for efficiency. So if we're aligning a read to the reference, nanopore reads can be 100,000 or even 1,000,000 bases long. So instead of doing O of n squared, 1,000,000 by 1,000,000 matrix, we already have the alignment. We're just trying to modify the fine-grained alignment around these repetitive regions. So if the red band shows the previous alignment, we can actually only look within 30 or 50 bases of that original alignment. And now we're doing 60 or 100 by 100,000 instead of 100,000 by 100,000. And there we gain a lot of efficiency during the computation. And now, so the main goal of introducing these lower gap penalties for repeated sequences is that now if we look at the aligned reads, it should realize that getting the length of this chunk of A's and the length of this chunk of T's incorrect, that was probably two separate events. So we probably added some extra A's here and dropped some T's here instead of preferring substitutions, because it doesn't have a kind of gap penalty for looking at repeated regions. So now if we look at the pileup, we can see that all three reads agree that there was an insertion of an A here.
Very good. I gotta go teach
Heading out. Okay,
527.
thanks for coming. So now on to the results. We measured alignment consistency using Gini purity, which is basically a squared summation of the probabilities for each of the categories. So if we're looking at a particular reference position, we split it up into insertions and then everything else, because basically the five other categories are AC, GT, or deletion. But insertions are kind of a special case because there's an infinite number of possible insertions at a position. So we had to calculate that a little bit separately. But if we first look at ACGT and a deletion, then to kind of give you an intuitive understanding of Gini purity, if all reads say that there was a C, then probability of C is 1, 1 squared is 1, so your purity is 1. If 90% of the reads said there was a C and 10% said it was something else, 0.9 squared is 0.81. So regardless of where the other 10% went, your purity is going to be between 0.8 and 1. If the reads are evenly split between C and G, then that's 0.5 squared plus 0.5 squared, which is 0.5. So that's going to be 50% purity. And anything less than that, your reads are very discordant and not really agreeing what happened. So down here on the bottom, we show, this is a logarithmic y-axis, so we can see that it's very common for reads to agree, orders of magnitude less common for reads to disagree that terribly. And green and blue are after applying our realignment, and red and yellow are before applying our realignment on the two haplotypes. It's hard to make out the amount of improvement that we've gotten. So on the top, I show the ratio per position of the reads that had that purity after realignment divided by prior to realignment. So we can see that from a baseline ratio of 1, we decreased the amount of reads with high discordance by a little bit more than 50%. So this realignment did improve how much the reads agreed at different positions. And then for insertion specifically, it didn't really make that much of a difference. So here's kind of an example of what the alignments looked like prior to and after to the realignment. And here, this is a very compressed, like 50 to 80 reads that were aligned to our reference. And there was a deletion at this position. So purple shows insertions, the black lines show deletions, and then anything colored is a substitution to that colored base. We can see that there were a bunch of A's and then a bunch of T's. And our realigner figured out that, okay, changing the length of A was independent from changing the length of T. So it aligns insertions and deletions to the start of those two regions respectively. Whereas Minimap, using the affine gap scoring, what it does is if only A's were inserted or deleted, then it puts them all left aligned. But if both A's and T's were deleted, then it prefers one gap over two, like I mentioned, because of the gap affine scoring. And as a result, it puts that deletion somewhere in the middle of the A's and T's. And then if there were substitutions, if there were extra A's and fewer T's, then it will be represented as substitutions from T to A, and same thing vice versa. So basically, instead of having a lot of different representations, it chooses to align them to either the start of the A's or the start of the T's, because statistically that's most likely what happened, because we're doing nanopore sequencing. And then if you look at the actual accuracy improvements for the pileup variant calling, typically they evaluate substitutions and indels separately, and they do precision recall curves. Here we kind of have two baselines, because the initial variant caller, Claire 3, didn't do read sorting by haplotype. So I added that to Claire 3 in order to get a more realistic red baseline. And then we can see that with the realignment in green, we improved substitution precision, and we improved indel precision and recall a little bit. And then this project is on GitHub if you want to check it out. I was funded by the NSF. And thanks everyone for listening.
And well, if anyone in the room has questions, again, feel free to raise your hand and ask questions. And if anyone online has a question, you can put it in the chat and we'll read it through to Tim. If you're in the room, if you can speak up, and Tim, if you remember.
Yeah, I'll try and repeat.
So you use this in the context of whole genome sequencing, and if I understood correctly, you train this what actually happened matrix on the alignment of the whole genome you're trying to sequence.
Yeah.
Have you started with changing what you feed it? If you're trying to focus on realigning things inside repeated regions, have you tried feeding it information specifically from those regions and seeing how that changes the output? I don't know if that would help at all, but it doesn't look like the benefit is not necessarily in the SMP rate, and like that's not the point of the
Yep.
change. The idea is to get those feed regions to be fixed. You could just feed it information from there.
Mhm.
Tried that?
Yeah, so the question was, basically when I calculate both the substitution penalties and later the repeated region gap penalties. Right now, I'm computing it based on the alignments to the entire sequence. The question was, would it help to compute those scores based on just the alignments to specific subsections of the genome?
Yeah, even like
Yeah.
segregating it by like 3 polymers, just 1 polymer.
Yeah, so the reason that basically I aligned it to the whole genome is so that basically you can get both the general substitution penalties and the general insertion and deletion penalties. So if you're in non-repeated regions, and then the N polymer lookup table, which is these matrices, they're only being, so this matrix, even though it's like aligned to the whole genome, the number of counts in each of these is only going to be incremented if there was actually like a repeat of chunk 3 of a certain length. So it's kind of this matrix is kind of already only looking at tandem repeat regions. Were you wondering like if there's
It's looking at tandem repeats like as they occur, but my
Mhm.
understanding is there are regions of the regions of the genome
Yeah.
in which that is a lot more common
Mhm.
than it is in other parts of it.
Yeah, that's a good question. So basically, right now it's kind of implemented so that basically like you provide a bed file to mask whatever regions of the genome you want to compute the statistics on. Basically, because like I was providing this as like a general case tool, I just did it for the entire genome. But yeah, you're right. Like if you're interested in like specific regions, then the really nice thing about like calculating all these like statistics and setting your scores based on what your data set actually contains is that you can just redo that if your data set or regions change. So it would totally be feasible to recalculate this for a specific subset of regions that you're interested in. Yeah.
There's a question online. Damien is wondering, what is the basic input for your software? Is it BAM files, DCF files?
Yeah, so the basic input is just a BAM. And if you want to recalculate the statistics, like that's an option, and you can provide a bed file for like where in the BAM you're gonna recalculate the statistics from. You can also just take the pre-computed statistics and you just give it a BAM and it gives you a new BAM. Just with like the small realignment changes. Yeah.
How stable your statistics are of calculating those analytics. If you switch the source that you can model it, is it going to switch like different?
Yeah, you're saying basically like these matrices, especially like for longer lengths. If you have like a smaller subset or something, it could be completely unstable. And how do you kind of make sure that the scores still make sense? So basically I kind of glossed over it, but I do apply some amount of smoothing and imputation to this matrix. So basically I enforce certain properties to make sure that all the scores still make sense. So basically I enforce like a few different properties. One is that if you have say a one base deletion, that's always going to be more likely from a longer homopolymer than a shorter one. And then a few different things, so that basically at lower repeat lengths, as long as you have like a reasonable region that you're sampling, you're going to get plenty of examples and good statistics. But you might not, for example, ever get an example of 4 polymer that was repeated 57 times. So basically some of those values are imputed and there's some amount of smoothing to make sure that all the values are reasonable. Yeah. I was also thinking about kind of like this affine gap scoring. People use like different functions for that. Some people, instead of just having like an insertion score and then an opening and extension score, they either like smooth that out into like something actually like logarithmic or whatever. So basically, instead of doing my own kind of like custom smoothing, I could also do some kind of best fit that would be like higher dimensional, but would also work. Yeah.
You have like a preset man for this polymers or
Yes, I think the preset, it's either 50 by 50 or 100 by 100. And then if it's longer, then I just take the value in like the last row. So like 50 by 50, and then just say, okay, the same penalty for the same amount of deletions as that. Yep.
Questions? Don't see anything else online either, so thank you for that.
Yep.
Everyone for coming, hope to see everyone next week.
oh, can you bring back the GitHub page again?
Oh, yeah. There we go. I'm gonna grab some pizza.
Oh,
I mean, that's what I'm gonna do for what I was at 6:15. We're just learning stuff that I learned in science, like 45. I think that's analysis. Yeah, that's why we took good notes. Wait, I'm not gonna keep doing that.
Thank you.
Yes. Yeah. And I know this one is, this one expires on the
Oh, it's
And
not.
yeah, whenever you drink a gallon of milk, you get a free water bottle. How nice.
Happy belated.
Yeah.
I know, because I thought
Yeah, I think you get So cheerful.
Yeah.
So, yeah.
I don't,
I know. We didn't work, we can chat.
Yeah.
You guys all want left?